All right. So hello everyone. Hope you had a good holidays. I'm gonna start with a few technicals, and then we're gonna move with the lecture. Okay, so the first thing regarding the material that you would need for the exam is going to be, it's a little bit updated since the last email I sent. So chapters 1 to 8, in your reading book, plus chapter 12. Now, chapters 7 and 8, and also 1, which you've already done, these are self-study. So I'm going to remind you again about these, but 7 and 8, please do read these chapters by yourself. Today, there's going to be no tutorial. I want to remind you also regarding the reading in general, so please do go over all the chapters that all the material that we've already touched into. So from 1 to 6, which I would be doing today, and 7 and 8, which you would be doing the self-study, and you can prepare also for 12, which is the last part of this course. I remind you also regarding the coursework. I put on Learning Central the assignment for the coursework. It's 3 courseworks, but it's basically in one. So it's supposed to be 3 points and 3 points and 4 points. So it's basically 10 points for the 3. So I just joined them together. That would be 10% of the total. I cannot recommend you enough to actually attempt these works, and start early. And if you have any problems, you can send me or Berna and discuss the problems. But I really recommend that you do this and submit in time. You would be notified how to actually submit. The submission deadline, I think, is 20 May. It should be on on Learning Central. The last thing, I also uploaded today a video on string paint oscillator, which has to do with something which is something I normally show here, but I found it now more convenient to do it this way because of this remote lecture. All right, so today we don't have much time really, because I want to cover 2 subjects. Anything that I don't cover in the lecture, please do cover by reading the relevant sections in the book. So today we're gonna talk in the first part about springs, Hooke's law, and simple harmonic oscillators. So we start with a spring. We have a spring. I actually have a spring here with me. This is a spring. I can take this off. You take the spring and you pull one part of it, right? And then it can start oscillating if I leave this part, okay? I can extend it to some distance here. I can extend it more. I can extend it more. I can feel in my fingers that the more I extend, what would happen? What do you think? You have a different force, right? So if I extend this much, I will have some force. If I extend more, I have more force, and more and more and more. Okay, so let's say we have a spring here. This is the spring. This is the relaxed length of the spring. And we extend that spring. We put a mass here, some mass M. And you can assume that this is on a table, but frictionless table, okay? There's no friction now. There's no friction. So it can freely oscillate from one side to another of the relaxed length of the spring. I leave it at that point. Well, before I leave it, actually, as I said, I can feel a force. There's a spring force which wants to restore it to the relaxed length. Okay, that's why it's also called a restoring force. So spring is a restoring force. I can also push it in this direction, and then the force would be in that direction. It's always in the direction of restoring the to the relaxed length. It's a restoring force. Now we can take this point as x equals 0, and this is an increasing value of x. This is my choice. And it is an experimental fact that the magnitude of the force is proportional to the extended length. So if I double this length, the force will double, and so on. So we can write force is a vector first. The case of force, as you know, is a vector. So in this case, we're going to talk about 1D to start with, 1D problem. So we can drop down all the vector notation, right? We can write F equals minus kx, right? This is the proportionality, right? This is x and f, and this minus k is the proportionality constant, which is known as the spring constant. Okay, and spring constant, you can immediately see the units, right? It's Newton per meter. These are the units. Now, why is this minus sign here? The minus sign here is actually telling me that it's a restoring force. Okay, so this is a restoring force. Whenever I'm on this side, it wants to bring me to the minus side, right? So the force is in the opposite direction. Whenever I'm here, so this is minus, minus is a plus, the force is in the plus direction. It's a restoring force. Okay. So whenever this holds, whenever this relation holds, F equals minus kx, this is called Hooke's law. It doesn't necessarily hold, but in a spring, that it holds as long as it holds, as long as we don't extend it too much. I'm going to talk about this a bit later. Then we call it Hooke's law. How can we measure that spring constant? The first thing we want to do now is quite easy. I can show you here the okay. I'll raise this up a little bit. Maybe a bit more. Okay, so what you have here, this is quite a nice spring. So it is following Hooke's law. Now you see it's more or less on the zero. And in order to calculate the spring constant, what we can do is start putting masses. Now we know what is the mass here. So this is a 10 grams mass. Okay, I can add a mass here. I can see by how much difference it goes. This is my x really. This is my delta x if you want. I can do, just for confidence, I can do this as many times as I want. And I'll come to this later on, put it on the side. So basically, what we start doing is building up this diagram with the force here and x here. I can calculate the force, right? It's simply m times g. I know the masses, and I can measure that distance x. So at some point, let's say we have a point here, and then we have a point here, and then a point here, point here. It should be a straight line. Why it should be a straight line? because if it's not a straight line, it's not following Hooke's law. If it's not a straight line, it means that this relation is not holding. Okay. So this is what we find. Now I can take this part here, for example, from here to here. This is my delta x, which I've measured, and this is my delta f, which I calculated. So k is delta f over delta x. It's that easy. Now, as you can see here, maybe you're not convinced. I just put one mass, so it went only 1 point. If what I've been saying is, well, if this is a Hooke's, if this is a Hooke's law type spring, then if I add the same mass again, then we're going to see that it always goes by the same delta x. Okay, so I did only 1 point. Now I want to go for another point and then another point. So it always should go by the same delta x. So let's see. It was more or less on the 0. And now it's more or less 1.5. So if this following Hooke's law, I can already predict that the next 10 grams that I'm going to put should take this to 3. Now let's see, roughly 3, right? Because, okay, and as you can see, it goes to 3. I'm going to put another one. It should go to 4.5. It goes to 4.5, right? And I can put, let's say, yeah, another one. And it goes to 6, right? I can put 2 more. It should go already to 9. I'm putting 2 more now. More or less. Okay, so it is a very nice spring. And if I take all of them, apart from the one that was there originally, then it should go back to 0. So basically, what we've been doing now, if you look at the board, we've been traveling along that line. Now we're traveling back, and it goes back to 0 almost. Okay. So as we've added, we went that direction as we added mass, and when we took mass off, we went back in the other direction. Now, you might have noticed that the spring was getting a bit too stretched towards the end, and you could actually take a spring and stretch it to the limit that you see it's completely deformed, right? So it doesn't go back to the original length. In this case, what happens is that initially, I'm going to do this in red. If you stretch the spring too much, pull it too much, then initially it would go following this line, but at some point you add a little force and that makes a big displacement. So this is what you're creating now. And this is irreversible. Now, if you leave it at that point, it would go back like that. So it's no longer in the same, won't go to the same length. Okay, let's see if we can also measure the spring constant in a dynamic way. Okay, so let's take a spring again on a table. And This is the table, it's frictionless. So we have the spring here. This is the relaxed length of the spring. I always like to call that x equals 0. You don't have to call it x equals 0. It's just I find it convenient. And we put a mass here. At that point, we put the mass and we release it. What happens is that it starts oscillating from one side to another, just as you've seen before. We have mg, and we have n, we have a force F. I'm going to derive this. So we use Newton's second law, F equals ma, so I can write ma equals to minus kx, right? Well, what is a? A is the second derivative of position in time. So I'm going to write it as mx with double dots. So instead of writing dx dt twice, so I have two dots here. So this is the second derivative in time. I'm going to bring this on the other side, plus kx equals 0, x double dot plus k over m times x equals 0 after dividing by m. What we end up is with this differential equation. You might already know what is the solution for this differential equation. But by solution, I mean we need to find some x of t. So we want to describe the position of this object at any moment in time. This would be what I call a solution. Okay. So we have the second derivative here in time, right? Should I write it down? Okay, x double dot is t squared x t t squared, just in case. All right, so what is the solution? The solution actually is in the video that I sent, so you can, if you're able to watch it now, you can watch it now. Otherwise, I'm going to just try to explain what is in the video, and then I'm going to write down the solution. But you can also watch it later on. It's not a big deal. So what we're doing really is we want to make this object oscillate. It doesn't matter if it's oscillating in this direction or in that direction. So this object is oscillating, okay? And as it's oscillating, I can attach to it some spray. Okay, let's put it from that side. So the spray spraying to that direction, which means now is if I have when this is oscillating up and down and it's spraying at the same time, let's say it's spraying in that direction, I can simply have a roll on this side and move it with a constant velocity, and that would give me the shape of the solution, right? That gives me actually the position of this mass, which is oscillating in time. And that solution is, you can try to guess if you want, and that solution is a sine or a cosine, right? So our trial function, or the solution for this, the solution here is x of t equals, now some constant that we're going to discuss soon. Let's move this out of the way. So the solution for this differential equation is, as I said, is a cosine or a sine. So amplitude times the cosine of omega times t plus phi. First of all, A is the amplitude. The amplitude means that, please turn off the speakers, unless if you want to ask something. Okay, the amplitude is would be the distance, maximum distance from the relaxed length that this can go. Okay, in this case, it would be simply here if I just release it with a zero velocity. However, I don't have to release it with a zero velocity. I have two choices when I release it, actually. I can either release it with a zero velocity, and that would be the amplitude, or I can give it some velocity, some extra velocity in that direction. So I can either push it in that direction or in this direction, and that would determine the amplitude. But that extra velocity that I'm giving is what is hidden here, which is the phase. This is the phase angle. Omega so omega, I can write, omega is the frequency, the angular frequency. And that is measured in radian per seconds. Don't confuse omega, the angular frequency, with the angular velocity. Both have the same symbol. This is the angular frequency. If you ever forget, you know that this is time. This should be dimensionless, which means this should be 1 over t as frequency, right? 1 over second, right? Radian over second. The period, we didn't solve this yet because we need to find out. This is a trial function, right? This is a trial function. We think it should look like that, but we need to show that it would actually work. Okay, I'll add this here. So t, which is the period, is 2 pi over omega. The period means the time that takes the object to go from that point back to the same point. Okay, doesn't have to be that point, it can be any point that it goes and make one complete oscillation. So the time that takes one complete oscillation is the period. And just to complete the picture here, you can also write the frequency in terms of hertz, right? So that would be omega over 2 pi. Okay. So it would also be 1 over t. I'm still in the board, yeah. And this has units of 1 over second or simply hertz. You've seen this already before. All right. So what we're going to do now, we're going to substitute the trial function into the differential equations in order to find the constants that we have there. Okay. So first, I can rewrite it here. So x of t is a cosine omega t plus phi. X dot, first derivative, would be minus omega a cosine, sine omega t plus phi. I'm going to talk about the phase angle later on. And then the second derivative is minus omega squared a cosine omega t plus phi. But what is this? This is x of t. So x double dot, the second derivative in time, would be minus omega squared a x of t. So here, x double dot is minus omega squared x. So all we need to do now is to substitute in the equation. We have x double dot. I add to that x over m times x, k over m times x. So we have minus omega squared x plus, I'll put this down for you, plus k over m times x equals 0. So for this to be satisfied, for the trial function to be satisfied, omega squared has to be equal to k over m, or omega equals square root of k over m. Which means, I go back to the period. The period now, if we make the substitution, right? Period is 2 pi over omega. Now we have omega here. We get 2 pi. And then, you can see this now. 2 pi square root of m over k, right? M over k. So we found the period of acceleration. Now, what's interesting here is that the period is independent of the amplitude. What does that mean? It means that regardless to how far you stretch the spring, as long as it's obeying Hooke's law, doesn't matter how far you pull the spring, it would always have the same period. So if I want to select, if I want to show you here, if this is the relaxed length and the object is here, let's assume that it would behave in this way. So the period would be like this: 1, 1, 1, 1 second. Okay, let's say that the spring makes it oscillate in this way. If I put it here now, it would still do 1, 1, 1. If I put it here, it would do 1, 1, 1. Why is that? Why is it that the period is independent of the amplitude? Now think of it this way: when you put the mass, when I just hold the spring at that point, right? I have a spring, and I just hold it at that point. There is a force at that point, right? I have the same mass here. I'm not changing the mass. If I'm pulling this more, let's say that the distance would be twice as much, right? What would happen to the force? The force has to go up. If the force goes up, then the acceleration in the system would go up. So the more you pull, the more acceleration you have. And at the end of the day, you get the same period. And it's quite intuitive. How about if you go very close to the x equals 0, that you actually, the limit goes to x equals 0. Think about that question. Would that still be obeying the what we've discussed here? So would this still be a solution also? Okay. The phase angle. The phase angle, I want to emphasize that when we release the mass at this point, we have the choice of releasing it without a velocity, but we have a choice of also giving it some initial velocity in either direction. And that velocity is reflected in the phase angle. Okay. Now we're going to do something similar in terms of this oscillation, which is called harmonic oscillation. It's a harmonic motion. It's a simple harmonic motion, actually. But we're going to do it with a pendulum. So we have a pendulum here. In a similar way, we're going to just leave the pendulum. Now we're going to leave gravity to make the work. Okay. And we want to see what is we want to actually derive at the end of the day the period, and try to compare between the two. It's not as simple as the spring. The first problem with the pendulum is we can't say it's one-dimensional, right? It is a two-dimensional problem, so that already shows that it has a potential of more complexity. So pendulum now. We release the pendulum from, now we have some angle here, theta. We know the length. We know the mass. And I would choose this as my x equals 0. I can choose this as y, and this is as the increasing value of x. The forces, now we have tension, right? We have T. We have mg. So we have T cosine theta. We decompose the vectors, T cosine theta and T sine theta. All right, so you have to look in both x and y directions. Let's start with the x direction. So in the x direction, F equals ma, and I'm already going to write mx double dot, so the second derivative in time, and that should be equal to, let's see, we have T sine theta. We have minus T sine theta. Minus, again, is because it's, well, you can see it, that is in that direction. But now if you want to read in terms of the physics, it's restoring the motion to the x equals 0 point. So we have a problem because t is not fixed. T is actually a function of time. It is a function of theta, right? When the mass is at this point, t is exactly mg, but when it's at some point there, it becomes smaller and smaller, right? So t is changing with time and also with theta, right? Theta is changing with time. And in y, we have my double dot, which is t cosine t, which is a function of theta, times cosine theta minus mg. This is in the y direction. Now, this is not so easy to solve. We cannot solve this as we've solved the spring problem. What do we do in this case, and what you should do also in the exam whenever you have this kind of pendulum, is that you make an assumption, unless otherwise the problem says otherwise. You make an assumption that the angle theta is very small. So you say, you know what? I don't want to solve for problems like this. I'm happy to solve problems like this. Small angle. You're going to see what is a small angle also. I'll give you a feeling what is a small angle. If you do that, so if theta is much smaller than 1, what happens is that we can make an approximation that cosine theta is about 1. That makes things quite simple, because if cosine theta is 1, and if theta is so small, then the movement in the y direction would be very small, which means that y dot, I'm going to write this here because it's part of the assumption that y dot would also be would be equal to 0. So almost no movement in the y direction when the pendulum, I'll show you. When eta is large, you have this movement, this much of movement in the y direction. But when eta is small, you almost have no movement in the y direction compared to the x direction. Okay, so y dot is assumed to be 0 as well. And now things become really easy, because if this is 0, if this is 1, first of all, t is no longer a function of theta. Here and here. Which means that t, I'll write it here, from y, we get t equals mg. It's just as if it was completely vertical. And this makes things really easy. Now, what happens to the sine theta? Now, cosine theta is 1. Sine theta, if you want to approximate for small theta, sine theta is theta. So this now turns into theta. I will rewrite everything and arrange everything for you. But before that, I want to give you a feeling of what is a small, very small theta. If you take 5 degrees, just to give you a feeling. So if you take 5 degrees, you get 0.996. If you take 10 degrees, you get 0.985. So even when you go to 10 degrees, the difference from 1, right? What I'm looking at is cosine theta. So cosine theta equals 1. This is our assumption. But if you take the exact cosine theta, so this is exact, well, not very exact, but up to 3 significant digits. So this would be the exact. This would be compared to 1. It's very small, right? Even when you take 10 degrees, you see that the difference is 1.5%. So we can ignore that for these problems. So now you can see that theta doesn't have to be 1 degree or half degree. It can be also 10 degrees, maybe 15 degrees. Maybe even more, depends on the application. Okay, so let's rewrite this in a nicer way. So basically we have now one equation really. The other equation is just telling me that T is equal to mg. I mean, one differential equation that we have. Okay, so from y, we know that T equals mg. And in the x direction, after, let's write it down, mx double dot. I'm going to bring everything to the left side already. So we have a plus. We had T sine theta before. And now we will have, okay, we had T sine theta before. And now we will have plus mg times theta. That's all. So plus mg times theta, but I'm going to make also one more step because what is theta? Think of the in terms of the distance here and L, right? So sine theta, which is theta in this case, equals to, I'll write it down here. So I'm replacing already, it's x over L, right? Sine theta is x over L. And sine theta is theta, so, okay. So we have these two equation and one differential equation. We see the first thing that we see, and this is equal to 0. The first thing we see is that this mass drops. You always should feel happy whenever the mass vanishes, whenever you deal with gravity problems, the pendulum and the gravity. If the mass is still there, you should know that something is wrong. But we will discuss this later on. So finally, you can write x double dot plus g over L times x equals 0. And this is almost the twin equation of what we had before. It's basically the same equation. It's just before we, instead of g and L, we had m and k. That's all. But it's the same equation, the same trial solution, the same solution. I don't even need to bother and solve it. I can just write down the solution. It's already x equals some x0 or a, the amplitude, cosine omega t plus phi. This is the solution, and we know that it works. However, omega here is the square root of g over L. And t, the period, is 2 pi square root of L over g. Let's focus on this, on the period for a second, just to have, again, some feeling of the physics here. What does that mean that we have the period is proportional to the square root of L? Which means that if I have a pendulum with length 1 meter, the period is about 2 meters. It's not meters. It's about 2 seconds. Okay, so t equals 2 pi square root of L over g. You can make this substitution, but The point is that if I want to get half of that period, the length has to be 4 times smaller because it's the square root. I'm going to show you. I have here the pendulum. This is about 1 meter. Okay, I'm going to hold it a little bit above so you can see the actual pendulum. I don't even care if it's 15 or even more, 30 degrees. I don't even care this time also about the air drag and resistive forces. Okay, let's see. 1, 2, 1, 2, 1, 2. It's about 2 seconds. So if I want now to create from this a pendulum with a period of 1 second, this equation tells me it's the square root of L, so it has to be, if the period is half, then the length has to be quarter. So it's 4 times smaller. So if I take now about quarter of the length, 1, 1, 1, 1, 1. Okay. So by looking at the equation now, try to develop the feeling of the physics behind it. And if things make sense, does it make sense that L is about here, which means that if I increase the pendulum, right, if it becomes extremely long, then the period also becomes extremely long. It's quite intuitive. If I make it shorter and shorter, it becomes the period becomes smaller. Okay, I can actually write here. So this is the pendulum. I can write next to it the period we had before for the spring, right? So instead of L over D, we have M over K. And let's see. Let's take a minute, maybe a few minutes, and see if things make sense. First of all, you see that there's no mass here. And we want to try to understand that to some depth. Why is it that you don't have mass here? Why is it that I say that whenever you lose your mass in the gravity problems, you should be happy? But you do have mass in the case of the spring. Why is it that the mass here and the K constant here and so on? Some of these are quite intuitive. But to start with the mass, if you take a spring, so this is for the spring. Let me write down. Okay, if you take a spring and you increase that, so you pull it more, or you take it at some point first of all, right? Let's talk about the mass first. So you pull the spring and you bring it to some point. You extend the spring to some point. The spring doesn't care which mass is there. The force is always the same at that point. The force has to do with the distance from the restoring point, right? It doesn't really care if you put 10 kilograms here or if you put 1 kilogram here, which means the force is the same. If the force is the same, but the mass is changing, is the force is the same and the mass goes up, what happens to the, now think in terms of Newton, F equals ma, what happens to the acceleration? It has to go down. If the mass goes up by a factor of 2, the acceleration has to go down by a factor of 2 because the force is not changing. So if I'm increasing the mass, the acceleration in the system has to decrease. If the acceleration in the system is decreasing, then it would take it longer to make the journey from one point to another. Now, I know you can see immediately that if m here is increasing, this is increasing, that's fine. But let's take it to the second level of understanding. If the mass is increasing, but the force is constant. Force is constant, why? Because the distance did not change. We did not change the distance. If the mass is increasing by some factor, the acceleration has to decrease by the exact factor. So acceleration goes down whenever mass goes up, and the other way around. And therefore, when the mass goes up, acceleration goes down, and the period has to become longer and longer. Now, let's take the pendulum. So we're still discussing the mass. In the case of the pendulum, if I double the mass now in the pendulum, the vertical component also doubles, right? If you double the mass, here, if I double the mass, the vertical component has to double as well. So the force is doubling. So if the mass is doubling and the force is also doubling, then A is not changing. So there's no change in the acceleration, right? So therefore, changing the mass cannot affect the period in the case of the pendulum. I'll say that again. We have a pendulum now and we put a mass here, right? And we want to understand why is it that changing the mass is not affecting the period? Or in other words, why is it that we don't see mass here in this relation for the period? Double the mass here. If you double the mass here, you see that the vertical component of the force also doubles. If the force doubles and the mass doubles, again, think in terms of F equals ma, the force is doubling, the mass is doubling, that's fine. A remains the same. Acceleration in the system remains the same. If the acceleration remains the same, which means that the period has to be also the same. Okay. Now, more intuitive things, if K, which is the stiffness, is the stiffness of the spring. If you increase K, what would happen to the acceleration? It would become, acceleration goes up. Or let's put it in a different way. Just let's do it in steps. If I increase K, I increase the force. I increased the force, but I did not change the mass. So the acceleration has to go up. If the acceleration goes up, what happens? The period has to go down. Okay? I want you to have these two levels of understanding. The first one, you can see this immediately here. You can read it immediately. You can say, oh, okay, you increase K, obviously T goes down. But physically, why? When we increase the stiffness of the system, the forces become larger in that system. If the force becomes larger, you're increasing the force. You did not change the mass. The acceleration has to increase. If the acceleration increases in this harmonic system, it means it will make the journey faster from one point to another. Therefore, the period would also go down. Gravity. That's easy to see if you just go to the outer space. If you go to the outer space and you have a pendulum and you just leave it at that point, it will just remain like that. But you can argue that it will take it infinite time actually to make one oscillation, right? And this is what you also read here. That G, as G goes to 0, that the period would become infinitely large. So if you want to measure mass And in your space shuttle, you have a place only for either pendulum or a spring. What do you choose? You choose the spring. You can't make it, unless if you make that, remember, the perceived gravity, right? But if you go to the outer space where there is no gravity and you want to measure the mass, you can measure mass with you can take this system in the space and you can measure the mass there quite accurately. Right? But pendulum won't help you there because it actually requires the gravity in order to have the harmonic oscillation. Okay, to conclude this part, I want to give you a solution, not the solution. I want to give you a problem for you to think about. If you think it's easy, think again. And if you think it's impossible, then think again. Imagine a pendulum now. This is the pendulum. But this pendulum is made of rigid arm. Okay, so this is rigid. And you put a mass here, mass M. The pendulum actually starts at location, this location. So you can call it at x equals 0. And it's not oscillating. It's just standing there. You can move it all around. So if you move it up to that point and you hold it, if you're careful, you can actually, unlike the pendulum that we had with the string, because this is rigid, in principle, you can actually hold it like this. This is L, and you have G. So you have everything that you need. You can neglect this is rigid, but you can neglect the mass. So this is some kind of a massless rigid arm. And the question is, how, if you can give it an initial velocity to make it stand exactly at that point. Okay, you give it an initial velocity here, give it a push, an initial velocity, some V0, and the target is to make it stand upside down exactly at that point. If it's a little bit more, of course, it would start going around forever. If it's a little bit less, it would start oscillating also around forever, from one side to another. So the target is to give it the right V0 such that it would stand exactly at that point. How long, or what is, well, how long would it take? I almost gave you the solution by mistake. How long would it take to reach this point P? To reach point P, the top point. Okay, think about it. It's not an easy problem, and it's not impossible as well. If you use what you've learned today, you actually might be able to solve it in seconds. All right, so this is the part about Hooke's law and springs. Do you have any questions before we close this part? Are there any questions? You can on your speaker if you have questions. All right. If not, let's take 2 minutes break, and then I'm going to continue with another subject. As I said, Berna won't be with you today. Unfortunately, he's not feeling well today, but we will compensate on that tutorial in one of the later on. All right, so let's take 2 minutes and we start with the other subject. All right. So we've been talking about moving objects, and for an object to move from one location to another, it requires energy, and some work needs to be done sometimes. Yeah. So to start with, we're going to define the work. So the work, can you see that? The work that an object makes from point A, point B. You can also think of it as a straight line later on. You'll see that it won't matter for the problems that we're looking at. What is the work? The work is the force which is doing along some distance, right? So F times the delta X. I'm going to do it now in a more accurate way. So it's that path that the force is doing along on all of these sections.
Hello.
Yeah.
Can you talk more about like the phase angle? Because I didn't really understand.
The phase velocity.
The phase angle.
The phase angle.
Yeah.
Okay, let me. I can't talk too much about it now because I want to talk a little bit about this. I'm not going to finish.
That's all right. Yeah.
All right. But I will just tell one thing now, and maybe in the next lecture we'll have more time to discuss it. When you think of the spring problem or the pendulum, you can think also of the pendulum. Okay, if I have that pendulum and I release it with zero velocity, then what I have is zero phase angle. Okay? But I can also release it with some velocity. And that some velocity, as you see in this case here, right, it would result also in the change of the amplitude. That would make some shift compared to if I started with that complete amplitude. That shift, which is caused by the velocity, is referred to as the phase angle. We will get to that more into detail later on. But I'm sorry I have to carry on with this. I don't want to hold you too long today, and also I have to go in about 20 minutes.
Thank you.
But you will have also enough problems with regards to the harmonic oscillators. So, okay, let's go back here. So the work would be the force. We integrate over the force along that path. And that is Newton times meter, which we refer to normally as joules. It's an energy unit. That work is energy. If there are multiple forces in the system, you simply add them together. Okay. But work itself, because you're adding all these together, is a scalar. The work is a scalar. F equals ma. F equals ma, and I can write A as dv dt. And x, or dx, is dx as v times dt. I want to substitute these now back here. See that? So the work between points A and B m dv dt, and dx is v dt, so I can write v dt here. Almost there. We get mv dv, which finally gives half mv squared between A and B. Let's write the final solution here. So it's half mv at point B squared minus half mv at point A squared. This is the work you can still see between A and B. So the work done between the points A and B is related to the endpoints only, A and B. So if I know the velocity at point A, I know the velocity at point B, I can say what is the work that has been done, ignoring gravity in time. Now this is called as kinetic energy. This half mv squared is called kinetic energy. You can see different notations. Don't let that confuse you. It can be K or KAE, doesn't matter. As long as you know its kinetic energy, you know it's half mv squared. Okay. So we can summarize now an important theorem actually, which is here, that the work between 2 points A and B made by that object equals to the kinetic energy at point B minus the kinetic energy at point A. And this is known as the work energy theorem. This is the work energy theorem. You tell me what's the difference in the kinetic energy between 2 points. I can tell you what is the work. Note that the work can be smaller than 0, larger than 0, or equal to 0. When it's equal to 0, it means there is no change in the kinetic energy in the system. When it's smaller than 0, it means there's a decrease in the kinetic energy. Right? The decrease, and this would be increase in kinetic energy. Let's take one example. I have an object. This is point A. This is point B. And the object is at point A. Object is at point A. We give it some velocity, initial velocity VA, and it reaches point B with 0 velocity. So at point B, PB would be 0. At any point here between the 2 points, this is Y. We have gravity now. So gravity would be minus mg and this distance between A and B, let's call it h. The question is, what is the value of h? So you throw A, and you want to know what is the distance at which the velocity becomes 0. But you might say, well, that's easy. I can use kinematics and I can solve that. That's correct. You can use that, and we've done that in the past. Now we're going to do it in a different way, using energy considerations. Okay, so the work that gravity is doing on the object is negative. This object is moving in that direction, and gravity wants to pull it in the opposite direction. So the work done by gravity is negative. Now the work AB equals to, if it reaches h to that point, then we have a minus mgh. So if the distance between point A and B is h, then the work would be minus mgh. But we also know that from the work energy theorem, that the work between 2 points is the difference in the kinetic energy. So the kinetic energy at point B is 0 minus the kinetic energy which is at point A, right? Write it here, minus mVA squared. This is the kinetic energy at point A. Kinetic energy at point B is 0. The masses drop, and we find H equals VA squared divided by 2G, which is what we found in the past. But now we found it in a different way using energy considerations. Let's look at a different problem similar to this one, but instead of having a velocity here at this point, I want to bring that object. So myself, I will take that object with V1 equals 0 at that point. I will take it and I will bring it to point B. So V1 is 0 and VV is 0. What is the difference in the kinetic energy? It's 0. So the total work has to be 0. Why is the total work is 0? Remember, I do work on the object and gravity does work on the object. Whenever I do positive work on the object, gravity is doing negative work on the object. So you can think of it in this way. So this is my work, which is plus mgh. Gravity's work is minus mgh. And if you add these together, is 0. Now this is an important point that you need to remember. If I have an object, I have this object, and I take it from this point to that point, I made some work. And then I bring it back to that point, I made the opposite work. So I would be making 0 work. I can do this many times. So I can do this hundreds of times, as long as I go from that point to that point and then back to the initial point. I can do that the whole day. And in physics, you would say I have done no work at all, okay? I can do that many times. I can get tired, but that doesn't matter. That still means that there is no work, because that's me positive, me negative, me positive, me negative. So the work that the total work that I would have done is 0. And also the total work on the object is 0, even if I just take it from here to here is 0. Because I do positive, gravity does negative. I do negative, gravity does positive. And it's the same value, right? So whenever I do this, in the case of that object, the total work on the object would always be 0. Okay, I have more things. I don't think I'm going to finish everything, but at least I want to minimize the amount that you would have to self-study by yourself, because we are short in time. Now let's do the 3D work. It's not complicated at all, actually. In the case of 3D work, we have an object and we want to move it now in 3-dimensional space. In 3-dimensional space, because we're decomposing everything, so basically what we would be doing is the same 1D problem, but with all the decomposed parts. So we have WAB. Now it goes from point A to point V. By the way, at the very beginning, I put AB like that. That was incorrect because actually I wanted to deal only with 1D problems, okay? So I apologize for that. It should have been only 1D problem, 1D motion. But you're gonna see now it doesn't really matter. Now we have it's a 2D problem now here, but you can think about it as 3D problem, okay? So we have a 3D problem, WAB, which is still a scalar, now will be defined in a very similar way. F would be vector now, and we would have some dr. Now dr would be this element length. Okay, dr is small element length. The force can be here like that, here it can be like that, and here like that. Doesn't matter. Okay, but this is a vector and that is a vector. So what is the force first? Force is Fx in the x direction plus Fy in the y direction plus Fz in the z direction. That dr can also decompose as some dx in the x direction plus dy in the y direction plus dz in the z direction. Right? A small element. You can look at the projections of the small element on x, y, and z. What would be a small element of the work? A small element of the work would be that Fx times the small dx, Fx dx, that's the small element, plus Fy dy plus Fz dz. All right, so now we can substitute back. We get omega AB equals to the integral from A to B, Fx dx. I'm just skipping, you could have them all together and then you can split integrations, right? So I'm skipping here one step. Fy dy. Let's say enough 1y. Let's have z here. Okay. All right, so all we need to do now is collect the terms here, and we know we've done this already before, right? We've done for this one, so it's going to be very similar. So it's going to be half m v va of that of x of point x. Let me just write it down. We're going to put half m outside, so we have v bx squared, so the element, the velocity element in the x direction at point B, minus vax squared, plus they're all going to have half, so let's put it like that, half m, plus vby squared minus the velocity at va squared plus vbz squared minus vb vaz. This is the penalty for trying to do things fast. Okay. Hopefully this should be Something is wrong. There is no BA. What is BA? It's BY. No, the penalty, apparently the penalty is too high. It's AY. Okay, all right. Now, what we can do is actually we can collect these terms together. What is this? V squared for in AX, AY, and AZ. You can think about it as the speed squared, right? We can collect these together, or we can collect these together. And we can write half m VB squared minus VA squared. Okay. All right. Let's see how much time. Okay, let's make this example and then with one more thing and then that's it. Okay. So example, we have the 3D problem. X, Y, Z. Remember, never forget X, Y, Z. Okay. We start with some point A. Let's say point A is projected here. It's point A. And we go to some point B. This is point B. We make a path. Doesn't matter. And we know that the distance between A and B in the y direction, we can call it h. So this is h. Yeah. Gravity would be we want to calculate the WAB. So we know that AYB minus YA is h. If the object is at some point, let's say here, have a minus mg in the y direction. So Fy is minus mg, WAB, FDR. You immediately can see that we know that the only thing that matters would be in the y direction from A to B here. So we have Fy dy. This is the only thing that matters, because gravity is the only thing which is making work here. And that is equal to minus mg yb minus ya, which is minus mgh. Apologize for going maybe too fast, but I want to at least to complete this part before we leave today. Now, whenever gravity is involved, you know that you can always look only at the end points when you want to calculate the work. And you can do that also for any force actually, which is called a conservative force. So when we deal with conservative forces like gravity, like springs, you only talk about the endpoints in order to calculate the work. But this is not true in the case of forces that are not conservative. One example of a force which is not conservative is friction. So if I'm moving this object here on the wall, now the friction is applying a work on the object. It's not applying the opposite work when I take it back, okay? So whenever we talk with friction, friction is not conservative. Whenever you talk about gravity or springs, then you can make use of what we have here. So if you have a problem that involves energy and work, and there's friction, you need to be careful if you're asked about the work. Okay, so we still have just gravity here, so I can still use this. Minus mgh equals to minus mg yb minus ya, right? This is what I had here. And this is exactly the kinetic energy, the difference in the kinetic energy between the 2 points, the end points, A and B. So I can rewrite this as mg yb plus keb equal to mg ya plus kea. And this is the second important theorem that I wanted to get to today, and this is called the work energy theorem. Now you have that mgy involved, and this is called the gravitational potential. This is gravitational potential energy. So basically what we have here is two things, gravitational potential and kinetic energy. Potential energy and kinetic energy. Now, sometimes people refer to that, write that as PE for potential energy, and sometimes they write U for potential energy. So again, don't let that confuse you. I'm going to write U just to make sure that won't confuse you. So I'm going to rewrite that now in a more compact form. I can simply write the potential energy at point V plus the kinetic energy at point B equals to the potential energy at point A plus the kinetic energy at point A. And this is conserved. Whenever you have these two together, we refer to that as mechanical energy. In the problems that we're dealing with above, this is conserved. So if the left side, if the kinetic energy goes up here, then the potential energy has to go down. Okay. Okay. All right. Last two small things. So one important thing when you talk about potential energy, the potential energy basically now, if I have this object here, if I want to increase the potential energy of this object relative to this point, I just raise it up. Now it has potential energy. Now you can think about the potential energy that if I release it at that point, it wants to go back to the lower energy points. If I release it from here, it wants to go down further. And the question is, okay, you've seen that mgy between two points A and B, right? mgy. How do you decide what is y equals 0? And the answer is it doesn't matter. As long as you're consistent, you can decide y equals 0 here. You can decide y equals 0 here. You can decide potential energy being 0 at this level, or being 0 at this level, or at that level. It doesn't matter. What's important is the difference in the potential energy. So if I decide, for example, u equals 0 here, then I would have u here, which is plus mgh. If I decide that u equals 0 here, then I would have u equal minus mgh at this point. The difference in the potential is always mgh. It doesn't matter at which location. So delta u is mgh. Right? And you can decide to have it down here. It doesn't matter. Same thing. All right. The really last thing now I wanted to show you. Well, what I'm going to show you is an example. It's actually a problem. I think you should find it also in the study book. Normally we solve it. I solve it in the lecture. It's about the race coaster. So we have a race coaster that goes like that, and then goes back. You start with some point here. If I start from point here with 0 velocity, I would oscillate up to some point there. Now I know actually, now I can tell you that I should get, without friction, if I start at this point here, I should get exactly up to that point, because this is my energy that I'm starting with. This is the potential energy that I'm starting with. I can go only as high as that energy. I can't get more energy because it's just a free sliding on this track. And the question here is, how high should we go? If I go, for example, to a point here, I might go up to some point here, but then fall in the middle here. Whenever you're going, this is circle, by the way. Okay, so this is a circular motion here. Whenever you see something like a circular motion and you have to complete the circle, the first thing that has to jump in your mind is centripetal acceleration, because the solution of this problem relies on centripetal acceleration. Let me just put the problem and let you deal with it. Now, because I'm not solving it, so it's a good potential for a problem in the exam. So the problem is like this. You start with some point here, which you don't know. You want to find out what is the distance, what is the height, h. Okay, what is h, or critical h? What is the critical h to make, just to make that turn? Obviously, if you go very high, then you can make that turn, and you can also go far away. But we want to know h that would just make that turn successful. What you know is the following. You know that the velocity here is 0, let's call this point B. Let's call this point C. At point B, you have some velocity. Why? Because you've lost some of your, think of in terms of the mechanical energy now, you've lost some of your potential in the favor of the kinetic energy. But together, they would be equal. They would be conserved. So you start with 0 here. So all you have is just potential, nothing else. At some point here, you've lost that much of potential. So you should have some kinetic energy here. So you have some VV. At some point here, of course, you have VC, and you have most of the kinetic energy. All the potential became kinetic energy. There's no potential anymore here. So this is the point where you have the maximum kinetic energy. Okay, that is VC here. Another important point, of course, probably the most important point, is point D. What happens at point D? Obviously, you should have some VD here. Now, given that the radius is R, so this whole thing here, if you want, is 2R. The question is now, what is H? And the hint that I gave you before is think that you should have a centripetal acceleration at this point. And you already know what is the condition on the centripetal acceleration on that point. If you use the condition on the centripetal acceleration at point D, then you should be able to get the critical H. So you're going to have H has to be equal or larger than in order to make the term. All right. Yeah, that's it for now. And as I said, please do the reading for this, for work and energy as well as for the rest of the sections. Okay, thanks everyone.